Have you ever wondered why large passenger aircraft store their fuel in the wings? At first glance, it seems counterintuitive. The fuselage has more space, better protection, and a stronger structure. But in aviation, decisions aren't made on intuition. They're the result of precise calculations. And storing fuel in the wings is one of the most deliberate engineering choices in an aircraft's design. The usual explanations are space efficiency. The fuselage is packed with passengers, cargo, and systems, so fuel moves to the wings, and the fact that wings have unused internal volume. Both are partly true, but don't reveal the real reason. If it were only about space, fuel could be stored almost anywhere. The real question isn't where fuel fits, but how its position affects the aircraft in flight. We're talking about distributing tens of tons of mass inside a flying structure, and the problem is where that mass will have the least impact on stability, control, and efficiency. Here, the center of gravity is crucial. If it moves too far forward, more control force is needed to maintain pitch. If it shifts too far aft, the aircraft becomes less stable. In both cases, control loads increase, efficiency drops, and stability suffers. So engineers carefully calculate how every major mass is distributed, and fuel is one of the largest. Unlike passengers, fuel is continuously consumed, meaning the aircraft's mass distribution changes throughout the flight. That's the core problem. The wings sit close to the region where lift is generated and near the allowable center of gravity range. As fuel burns, the balance changes only minimally, so the aircraft stays stable and efficient without constant corrections. But that's not all. From the outside, a wing looks thin and empty, yet it's a complex load-bearing structure of spars, ribs, and elements that define its strength and shape. Between them is significant internal volume that already exists as part of the structure. It doesn't need to be redesigned. The fuselage, by contrast, is the most valuable space. Passengers, cargo, and critical systems live there, and every cubic meter affects flight economics. Using it for fuel means losing payload. The wing has no such limitation. That's why aircraft use a wet wing design. The wing itself becomes the fuel tank, sealed, segmented, and designed so fuel moves smoothly. This uses a large volume without increasing the aircraft's size or sacrificing payload. There's another factor that makes the design truly elegant. In flight, lift pulls the wing upward along its entire span, while most of the aircraft's mass, fuselage, passengers, cargo, is concentrated in the center, pulling downward. The wing behaves like a cantilever beam trying to bend upward. If the wing is empty, the bending moment and stress at the wing root, the most critical structural area, increase. Fuel distributed along the span acts as a counterweight to the lift force. The wing bends less, stress is reduced, and material fatigue decreases over time. Fuel isn't just energy. It's part of the aircraft's structural system. Consider the Boeing 737. It has 3 main tanks, 2 in the wings, and 1 central tank in the center wing box. On short and medium-haul flights, it uses only the wing tanks. The center tank is used when extra fuel is needed. A key rule: if there's fuel in the center tank, it's used first, controlled by the fuel system's feed priority. Once the center tank is empty, the system switches to the wing tanks. The reason is simple. Fuel in the center adds load closer to the fuselage, so engineers remove that mass as early as possible. Even the fuel burn sequence is designed to maintain optimal balance. Aircraft are refueled through a dedicated port, usually under the wing. Fuel goes first into the wing tanks, then, if needed, into the center tank. The process is calculated in advance based on weight, distance, and safety requirements. The fuel is aviation kerosene, a highly standardized mixture that must stay fluid at extremely low temperatures, resist crystallization, and burn consistently. Fuel systems are built with multiple layers of redundancy. Each tank has multiple pumps, backup feed modes, and systems that reduce the risk of vapor ignition. Sometimes an aircraft must dump fuel in flight. The reason is weight limits. Aircraft have a maximum takeoff weight and a maximum landing weight, and the landing weight is always lower. If a plane must return shortly after takeoff, it may be too heavy to land safely. Then there are 2 options: stay airborne and burn fuel, or dump it. Some aircraft have dump systems that release fuel through nozzles near the wings, where it disperses into fine droplets and rapidly evaporates. It's a rare procedure used only when necessary, performed at high altitude where the fuel atomizes and evaporates, rarely reaching the ground as liquid, and strictly regulated. The most important systems are often the least visible. But engineering becomes especially obvious at landing. A machine weighing hundreds of tons approaches the runway at around 250,270 kilometers per hour, the speed of a racing car, then touches down on relatively small wheels that look tiny against the huge fuselage. Why don't these tires explode? A regular car tire would likely fail almost instantly under such conditions, and aircraft tires aren't filled with ordinary air. The answer lies in the tire's construction and operating conditions. At touchdown, the wheels aren't spinning. In the air, they hang almost motionless. The instant the tires touch the runway, the wheels must accelerate from 0 to the aircraft's speed, around 250 kilometers per hour, in a fraction of a second. Until they spin up, the tires slide along the runway, which is why you see puffs of smoke right after touchdown. Intense friction, not a malfunction. In those first moments, the tires face the aircraft's massive weight, intense friction, rapid acceleration, and heat buildup, with surface temperatures reaching 150 degrees Celsius. Weight distribution matters too. Aircraft seem to have few wheels, but there are more than expected. Medium aircraft typically have 6, 12, large airliners 14, 22, and the largest even more. An aircraft can weigh 300, 400, or even 500 tons at landing. And if a few wheels carried that, the pressure on each would be enormous. So engineers spread the load across many wheels. The aircraft also doesn't touch down on all wheels at once. The main landing gear, under the wings or near the center, touches first and carries about 90% of the weight. The nose gear touches down a moment later, mainly helping with steering and stability. What are aircraft tires made of? They look like car tires but are far more complex inside. A multi-layer structure where each layer has a function. The outer part is special synthetic rubber that withstands stress, friction, and heat. But rubber alone isn't enough. Inside are nylon cord layers, strong fibers that keep the rubber from stretching or tearing under load. Reinforcing fibers distribute pressure evenly, and steel belts give the tire rigidity and help it hold its shape. Thanks to this construction, a single tire supports tens of tons while staying flexible enough to absorb the landing impact. Another factor is the extremely high pressure inside. A car tire is inflated to about 30.35 pounds per square inch, but an aircraft tire can exceed 200 pounds per square inch, roughly 6 times higher. So why aren't they filled with ordinary air? In reality, they're almost always filled with nitrogen because of the extreme conditions. On landing, the tires heat up rapidly from friction, while at altitudes around 10 kilometers, the outside temperature can drop to about minus 50 degrees Celsius. Under such conditions, ordinary air would behave unpredictably. There are several reasons for nitrogen. First, it contains no moisture. Ordinary air holds water vapor that can freeze at high altitude. Second, it contains no oxygen, which over time reacts chemically with rubber and metal, accelerating degradation. Third, nitrogen pressure behaves more predictably as temperatures change, staying stable as the tires heat up. And finally, nitrogen is safer. It doesn't support combustion, making the system more stable under high heat and heavy loads. It's the combination of all these engineering solutions that makes the seemingly impossible work. Relatively small wheels are able to absorb the landing of an aircraft weighing hundreds of tons while traveling at more than 250 kilometers per hour.